during the presentation, I will weave in a narrative of the other talks that are in this session. I'll begin by sharing my screen. And I'll ask, first of all, if all participants can see the screen. If so, please give a thumbs up. I see thumbs up. Very good. Thank you so much. In interest of bandwidth, I'm going to turn my video off. Good. Welcome everyone once again. This session is entitled The Early Earth, Environmental Conditions and Early Organic Molecules. As you see, the session is a potpourri of different topics that touch on aspects of environmental conditions at the time of life's emergence. Now, I put a little arrow over here because I see a lot of synergistic relationships with the session that will occur tomorrow. So I encourage those of you who are here to take both of these sessions very carefully in your questioning process, and then of course consider attending all of these, because I think they're going to be very, very interesting and informative. My presentation today is entitled Exogenous Effects, Bioessential Inventories, Rocky Differentiated Planets and Life. And that's already a lot. And so I want to get started immediately by sharing with you what I would like to talk about today. There were discussions yesterday, extremely interesting discussions of the chemistry of the interplanetary and interstellar medium. But my focus will bring us back to planets and life. And in particular, looking at the Hadean Earth as a template for this life. Now, it is the natural laboratory that we can augur by going to field areas and collecting rock samples, as we heard yesterday from the very nice presentation by Emmanuelle Javot, who was the keynote speaker for the whole meeting. And as she pointed out for us, there have been modifications to and augmentations of this template. So my interest is in dynamical modifications to the template for the origin and propagation of life on Earth, and indeed of terrestrial planets. So hopefully I will succeed today in giving you a synthesis of my recent ideas on these matters. And if time permits, I will talk about planets long gone that nevertheless give us clues about the bioavailability of elements in the cosmos. And then I will end my presentation with some musings. So, opening thoughts, I want to borrow a famous quote from Dobzhansky, who's shown right here, who is well known for saying that nothing in biology makes sense except in the light of evolution. Life, that's a that's a mistake there, except in light of evolution. Well, as a geologist, I'd like to think that nothing in the study of planets makes sense except in the light of the evolution of the elements. And Stanley Miller used to say that the origin of life is the origin of Darwinian evolution. Well, I would like to add to that a plausible corollary is that the origin of evolution may be the origin of information, as shown here in this famous structural diagram of Watson and Crick. But the crustal platforms of planets like the Earth and possibly Mars and terrestrial type exoplanets, which we shall begin seeing next year once the James Webb Space Telescope is launched and in place. It is designed to collect data on such exoplanets. And I think that rocks indeed provide this ultimate informational template. And my favorite scientist of the 20th century is Marie Skłodowska-Curie, who also was a great fan of minerals. And she would share with you that the Lomonosov bridge between the non-living and living world is probably bridged by minerals. And to understand the propensity for a biosphere to exist, I would argue that we need to understand planets. And to understand planets, we need to study both rocks and stars in an integrative way. And that leads to a new kind of science, which I like to term geoastronomy. Now, as a geologist, I look at planets not just as balls of rock, say around a star, but as active, dynamical, chemical systems. Now, life in such a chemical system, of course, comes about as long as you have liquid water, organic chemical building blocks, and free energy from disequilibria available. And something that is often neglected, but I think is important, is time, because you need to have time in order to have all of these ingredients together in a planetary surface to react with one another. And for those of you who haven't turned off your microphone, please do, because it interferes with the voices in my head. The hypothesis, though, that life will arise when these four conditions are met is faced with the fact that the hardest steps were probably the first ones, as our inimitable friend Mike Russell would remind us. Now, our solar system neighborhood of the Earth and Moon and Mars have long been our test beds for trying to make sense of the origin of life on this planet. The curious case of the Moon, though, is that it really has defined a lot of our thinking of the subject of conditions on the early Earth, even though our sample area of the Moon is less than 12% of the geology of that surface. Indeed, the Moon is peculiar. The area that was sampled here is unusual in its composition. It's very high in thorium, uranium, potassium, and so forth. So it is by no means any measure of the geology of the Moon. However, our understanding of the Moon leads us to a better understanding of the conditions of Earth's formation at about the time that life began. Because to make the Moon, it seems, you need to have a giant impact. Well, the Earth-Moon impact was enough to vaporize the planet, and this happened approximately 50 million years after the start of the solar system. That event chemically reset our planet. It supplied about 4 × 10⁻31 joules to the proto-Earth, and per kilogram, that's about the low pressure heat of vaporization of rock. Now, the way you try to understand this is you melt the whole Earth and then you solidify it again. Well, you do that by cooling, but cooling takes time. First, you have to dissipate an optically thick atmosphere. You have to bring the surface heat flow way down, but at this rate of cooling, the atmosphere collapses in about 2,000 years, but a supercritical atmosphere remains. Heat transfer from the mantle to the atmosphere to space is controlled by something like this, molten rock. But once you solidify this molten rock, convection beneath and heat loss therefore slows, because the crust is an effective and highly reactive thermal boundary layer between the mantle and the atmosphere. And cooling takes about 10 million years before water could condense on top of the surface. But when it does, that surface is very, very reactive. If we take the Earth's peridotite composition and freeze it, we get a rock kind of like komatiite or basaltic komatiite. In connection with water, this reacts to make serpentine plus magnetite and many, many other minerals associated with a group of rocks called serpentinites. These highly reactive rocks are very rich in magnesium and high in nickel, chrome, and cobalt. It is very dense, but at hydration, it increases its volumes by about 30%, and it becomes very pliable. Well, this is a part of the subject of the talk that you will see at 12:45 Eastern Time by Bill, called The Origin of Life or Origin of Microbes. And in Bill Martin's talk, he discusses minerals associated with serpentinite, such as greigite here, magnetite, and awaruite, which you can hear more about in his talk. Meanwhile, speaking of metals, there's a group of metals, precious metals, called the highly siderophile elements. Now, in the Earth, these are unusual because they're at unusually high concentrations in Earth's mantle. They're about here relative to chondrite normalization. Now, these elements really should have gone into Earth's core, and they should be down here in abundance. But they're something like 1,000 times more abundant than they ought to be because of partitioning rules between metal and silicate. This overabundance and the fact that the overabundance is in chondritic relative proportions has led people to propose that the Earth was struck by another object after the moon forming event, sometime after 4.51 billion years ago, that donated these metals to Earth's mantle. That object, which has been dubbed Moneta, is simulated here in a collision with the Earth by a moon-sized object at about 90 degrees relative reference frame, 30 degrees, 45 degrees, and 60 degrees. The important point of these experiments, which you can find in this paper here, is that the outcomes are amazing. They're very, very different from the moon forming impact. These sorts of impacts are small grazing impacts where the impactor actually breaks up and fragments and rains back down to the Earth, as shown here in this strain diagram. In strain rate versus number of impactor particles, you see that fragment sizes are somewhere in the range of 10 meters, raining back onto the impacted Earth's surface. This kind of condition here, shown in these red dots, leads to a metallic hail delivered to the Earth's surface subsequent to the moon forming impact, before the age of the oldest rocks on our planet. We've investigated this as an apparent source of a transient reduced atmosphere in the early Hadean Earth, because the amount of metal that would be delivered by an object striking the Earth of this mass is enough to reduce about 3 ocean masses to a hydrogen atmosphere of approximately 80 bars, expressed as surface atmospheric pressure. These are well-known reactions, the reaction of metallic iron with water, either yielding wüstite here, which accounts for about 8% of the Earth's mantle FeO, or in this case, magnetite. Mars was also affected by such a late Vernier scale colossal impact, as shown in this paper. It was struck by a Ceres mass object about 1,000 kilometers in diameter, dubbed Nereo. The yield of Nereo's mantle reacting with water or oxidized mantle at the surface is about 0.7 bars of hydrogen. These events may also be responsible for some of the geomorphic features found in Mars's crust, including this dimple that's in the northern hemisphere of Mars called the Borealis Basin. Now, independent lines of evidence for such effects on the crust of the Earth have been seen for a long time, except we didn't understand what they were. Right here is shown the lead isotope evolution curve for the Earth, showing Canyon Diablo and various Earth materials. In lead isotopes, the slope of this line provides an age that is consistently younger than the meteorites, at about 4.48 billion. The same age is derived when one analyzes terrestrial xenon isotopes from the decay of uranium. That gives an age of xenon in the atmosphere of 4.48 billion. We've been looking at these data for almost 40 years, And it wasn't until recently that we could see that this is the last time the silicate reservoirs of the Earth were separated. It's the last time the Earth experienced wholesale crustal melting, probably from this late veneer event. Now, what about late accretion, all the time after this late veneer impactor?
You might be really interested in this.
Okay, I'm glad someone's interested in it, and thanks for letting me know. I appreciate it. Back to the Earth and Mars and the Moon, however, we realized that if their crusts were melted, like in the manner that I demonstrated to you right now, they are too modified to tell us anything about the time in the solar system before 4.4 billion years ago. So instead, we have to go to an archive that is older, and that is the asteroids. The asteroids predate the formation of the terrestrial planets. We have 60,000 samples of asteroidal meteorites that come from approximately 120 different parent bodies. Some of these, like here, this is Vesta. We have about 900 samples of Vesta in the form of HED meteorites. And the Lucy mission, which was just launched last week, will be visiting the Trojan asteroids here nearby Jupiter. And Bennu and Ryugu are other asteroids for which Jamie L. Cielsa yesterday told us about in the sample return mission that we should all look forward to hearing more about. Now, if we look at the ages of these asteroidal meteorites, there's something peculiar about them. We can look, for instance, at a particular rock, asteroidal meteorite, and look at different minerals in that rock that have different closure temperatures in their radioactive systems. Minerals like apatite, which are very sensitive to thermal resetting of their ages, versus other minerals like zircon here, which are not very sensitive. They're very robust to resetting. So we can use the asteroidal meteorites to test whether or not we see a planet formation only thermal event of the asteroid belt, which would show up just here in age, where only tough to reset minerals are reset and easy to reset minerals are reset all of the time, or something like a late heavy bombardment event over here, which we heard a little bit about yesterday in Furukawa's talk. Another possibility is that late accretion since the moon forming and since the late veneer events has been smooth, showing this sort of smooth decline here. So we can look in the meteorite data to see which of these three scenarios is satisfied by the data. So that's what we plotted here in a paper from a couple of years ago, where hard to reset minerals show all of these very old ages, and easy to reset minerals with low closure temperature like these in the argon-argon system are shown here. I think it's pretty obvious that you see a cascade type pattern in these data. And that is precisely the kind of data stream that we would anticipate in a long monotonic decay in late accretion. And furthermore, this is a topic, for instance, with which our colleague Nicole Zellner, who I see is in the audience, has also investigated with respect to the late heavy bombardment in lunar samples. Now, we have analyzed this further by running dynamical simulations of late accretion. And here shown on this axis is the eccentricity of each of these orbiting particles in terms of millions of years. And this is Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And we allow these particles to evolve. And over time here, we track their impact to the different solar system planets. And when we do that, we have an inventory of impact rates, for instance, onto the Earth and Moon, that we can use to test whether they satisfy the cratering record and the geochronological record that I described for the asteroidal meteorites. An important take-home message for everybody here is that the dominant material coming in here to the Earth is in this group, relatively late, which seems to also be dominantly from a group of meteorites called the ensotichondrites. The innermost part of the asteroid belt gets cleared out, and it gets sent to the inner solar system and contaminates, for example, the Earth. So here's the Earth now, as this is an animation from my colleague Simone Marchi in Boulder. And this Earth gets hammered by these objects. But you're going to hear more about what early Earth's atmosphere looked like in the talk by Paolo Sossi at 1:15 Eastern Time, where he shows experimental conditions that indicate the secondary atmosphere, the outgas atmosphere of the early Earth was CO2 dominated. But late accretion effects to the Earth were profound. And if we accept this late accretion scenario for the Hadean eon from various sources, in this case, from the later part of this accretion being dominated by this ensotichondrite group, then we can begin to simulate the thermal conditions of the Hadean Earth's crust, as shown here in this animation. This is time in millions of years before present, 4.5 billion years ago to 4 billion years ago. This is the percent of crust that's molten at any particular time using the mass production functions of that late accretion that I showed you, tied to the cratering record and harmonized with the geochronology of the asteroidal meteorites. Now, that's interesting and important because it shows that production of molten crust by late accretion bombardment could be significant, something on the order of 20% of the crust at the height of this late accretion would be in the form of glass. And glass of highly mafic composition is very, very reactive with water, and it will immediately serpentinize. Now, according to our analysis, before about 4.48 billion years ago, there don't seem to be any cases where persistent niches for origin of life could occur. After about 4.4 billion years, however, there seem to be no obvious barriers for the origin and propagation of life on our planet. Now, you'll hear more about those conditions and also how impact conditions can lead to interesting and relevant organic chemical processes on the early Earth in the talk by Vanessa McCaffrey at 12:30 Eastern Time. Now, something that we took advantage of in these analyses is to look at the supply of phosphate that would be delivered by this group of meteorites called the ensotichondrites. And that was presented last year in this paper with Dougal Ritson and John Sutherland. And this is the delivery of phosphorus by late accretion in kilograms per year. By the way, a topic that you will hear a lot about tomorrow in Matt Pasek's talk. Now, that's interesting because it isn't just phosphorus that gets delivered to the Hadean and early Archean Earth. It's lots of other elements like sulfur, but in the form of mostly iron sulfide. Carbon, mostly as carbonaceous matter that gets heated. It's very sensitive to heat, I should say. Phosphorus as phosphide and phosphate, which again, you'll hear more about tomorrow, but also this one, nitrogen. It's mostly delivered in EC chondrites as nitride, like silicon nitride. Silicon nitride has a melting temperature of over 2,100 Kelvin, but in supercritical water, it yields ammonia. And as pointed out in this paper, for instance, by Thibuni et al. In 1989. This kind of delivery of material is something that we can look for because we have samples of rocks here, like in the Acasta Gneiss complex in northwestern Canada, or in the Nouveau Agetuk complex in northern Quebec, and so on, where some of these extraterrestrial materials might be present in the oldest sediments. Now, this sort of condition of water in contact with rock and so on and chemistry is something that is germane to spontaneous structural developments, which you'll hear more about in Christian Meyer's talk at 1 p.m. Eastern Time. Now, something that concerns me as a person working in impact physics is that the thermal survivability of materials delivered by accretion is not very good. These materials can actually be heated to quite high temperatures. For instance, this is some work by Artemieva from almost 2 decades ago, but the science is the same. Look, temperatures even of a Tunguska or tektite generating type airburst or a tektite ejecta impact here with an impact basin diameter of only about 20 kilometers. For about 10 seconds or so, you're in the 2,000 to 3,000 Kelvin range in an impact plume here. Now, that's of course interesting because distance from impact, things are going to cool very quickly, and you will have survivability of solid target material shown here in these dark dots in a strewn field that may go hundreds of kilometers downfield from the impact site. So I think that there's something to be said for the problem of survivability of materials delivered by accretion. Now, I was going to see if I had time. I have 5 minutes left in my presentation, and I want to leave some time for questions. But I wanted to go back to the fact that we do not have a diagram like this for planets. This is called a Hertzsprung-Russell diagram. It's a diagram for stars where you have the temperature of the star against how bright it is. And this is where our sun sits. Our sun is a G-type star. So these are K stars here. They're sort of orange. M stars shown here. F stars are here, and so forth. Well, planets that are long gone may give us some clues about the composition of solar systems elsewhere. And one class is found in around a group of stellar objects called white dwarfs. One of these white dwarfs, some years ago, Mike Jura found evidence of contamination of the dwarf by planetary debris. And so these dwarfs are small. They're the mass of the sun, but close to the radius of the Earth. They're peculiar because they are the product after the blown out most or all of the planets in its inner solar system, maybe leaving some debris on the outside. And metals that pollute the outer crust of a white dwarf should be visible in spectra. And indeed they are. Here's some beautiful work by Hollins and others that shows here potassium against sodium, a moderately volatile pair of elements, against calcium against sodium, a moderately refractory element. So these two white dwarf polluted surfaces are shown here, and our sun is shown as an example. But if we were to plot the Earth and Earth's continental crust here, it doesn't plot really close to that of these white dwarf pollutants. And if we try to plot the terrestrial planets there, it doesn't look like the white dwarf pollutants here could be explained by terrestrial planet type contamination, nor could they be explained by chondritic meteorite type contamination. However, they can be explained by the composition of comets. Comets like Comet Wild 2 here are pretty close to the field of analyzed white dwarfs. And I think that that is the expected result because Jovian type planets and even cometary debris may be the last thing to survive in a solar system, and really is the end product of our own solar system. So that's a little foray into extrasolar chemistry, but I wanted to end with some musings about habitability. Now, habitability has no formal classification. I think it's loosely defined and doesn't even represent the cloaked oceans of worlds where probably most of the habitable volume of the universe is located. Most of our experiments on the origin of life actually work under a regime of familiar Earth life. I also think there are no obvious chemical and thermal barriers to the origin and propagation of life on Earth since 4.4 billion years ago, and biophilic elements are not in short supply. Elements for life like these are common in the cosmos and have a common heritage over galactic chemical evolution. That's the end of my talk. I want to acknowledge many people, including my colleagues Ramon Brasser and Maria Lugaro here in Budapest, and colleagues Craig O'Neill and Rob Spargarten and Haiyang Wang elsewhere. And also to thank you, the Scientific Organizing Committee, ISOL colleagues, conference attendees, and especially students, postdocs, and junior researchers.